Okay, hello. These are the practice problems for chapter 11 and also chapter 12 for dynamics. So for question 1, we have this figure associated with it. So I will just make that bigger, and then we can send it to the front. Okay, there. So we have this diagram here. So we have a rigid drum can rotate about a fixed frictionless horizontal axis through its center, right? So this is the drum. There's a frictionless axis through the center horizontally, as shown in the figure. Rope 1 is wrapped around the inner hub of radius R1 equals 0.4 meters and supports a block of mass M equals 20 kilograms, right? So rope 2 is wrapped around the outer rim of radius R over 2 equals 0.8 meters. System is held at rest at time t equals 0. Constant force F equals 300. Newtons is applied to rope 2, causing the block to move up. Drum has mass M equals 60 kilograms and radius of gyration K equals 0.55 meters. Assume the ropes are massless and there's no slip between the ropes and the drum. Part A, draw the free body and kinetic diagram. So this is easy, right? We're going to have our free body here, and we're going to have our kinetic diagram here, right? So this is for the block, not this rope here. So on the block, we have a rope going up, so we have a tension force, and then we have weight working down on it. Now, for a kinetic diagram, it says here that the force causes the block to move up. So our acceleration is going to be upwards like so, right? And we're going to take up to be our positive. So we have set up our coordinate plane, we've drawn our free body diagram, and now we can actually solve the question. So B is determine the angular acceleration of the drum. So to solve this, we're going to start with the fact that the sum of the torques is equal to I alpha, right? And what torques do we have, right? Also, we're going to be considering counterclockwise. So we should have this on here, counterclockwise to be positive, right? Just, that's the, usually you take counterclockwise to be positive. Obviously, it doesn't matter, because it's like your own interpretation. The algebra will give you the same thing, just like a negative answer. If you assume clockwise to be positive, then you get like your final answer would be negative if it's not the other, if it's counterclockwise, right? So anyways, as I was saying, so we're going to have one moment is going to be, and we're taking the moment around this center here, right? So we have one moment caused by this rope. And what force is on this rope? Well, it's tension. And tension is acting like this direction, right? And we have one force here, F, which is acting in this direction, so counterclockwise. So we have, for our sum of tau, we have I alpha is equal to F R2 minus T R1, right? And this is a formula I didn't actually go over in the theory videos, but we have this one here, the radius of gyration, right? And you'd solve it like this: K equals root I over M. So if we rearrange for I, right, we get mk squared. I is equal to mk squared, right? So we have I is equal to mk squared. And this is a capital M because we don't want the mass of the block. The block doesn't have the radius of gyration. The drum has it, and the mass of the drum is 60, right? So this is just equal to 60 times 0.55 squared, 60 times 0.55 squared. So this is equal to 18.15 kilogram meters squared. Kilogram meters squared. And, well, you can check this pretty easily, the units, right? So now we're going to solve, we're going to take this equation, and we're just going to plug stuff in. So we have 18.15 alpha is equal to, so force is 300, radius is, R2 is 0.8, right? Minus, and R1 is 0.4, 0.4 T, right? We have two unknowns here. And if we can simplify this, 300 times 0.8 is 240, right? So 240. Now we have two unknowns, as you can see. So we're going to have to get another equation. So how can we get another equation? Well, looking at our free body diagram, right, we have T minus mg is equal to ma, right? And what do we know about A? Well, we know that A is equal to R alpha, but which R? Well, if we look at it, it's going to be R1. So it's equal to alpha R1, like so. R1, right? So we can plug that in. We get T minus mg is equal to m alpha R1, right? And if we were to now simplify this for T, we get T is equal to, so mg is, m is 20, g is 9.81, right? So that is going to be 196.2, right? Alpha R1 is 0.4, m is 20, so 20 times 0.4 is 8. So we're going to get that T is equal to 196.2 plus 8 alpha, right? And then we're going to take this T and we're going to plug it into this equation, which gives us 18.15 alpha is equal to 240 minus 0.4 of this, right? So now when we solve for alpha, we're going to distribute out 0.4, which gives us 240 minus 0.4 times 196.2. And then we're going to have negative 0.4 times 8, which is something alpha. And then we're just going to, this is minus, we're going to add it to this side and then divide by the sum of this, which gives us an alpha that is equal to, so let me just get this into my calculator here. So 240 minus 0.4, 196.2. Okay, it's equal to this. And then divide by 18.15 plus 0.4 times 0.8. Times 8. Which gives us a alpha, which is equal to 7.56 radians per second squared. Right? And we're working in radians here specifically. You could do degrees if you wanted, but these formulas, you'd have to convert it to degrees by, what is it? Divide by pi times 180. Yeah. So multiply by 180 over pi if you wanted to convert to degrees per second. These formulas output radians per second. So keep that in mind, right? So that's how you solve for B. Now C is find the acceleration of the block. Well, we already know that acceleration is equal to alpha R1. So we're going to take A is equal to 0.4, which is R1 times 7.56, right? And this is meters per radian, right? And this is radians per second squared, which gives you an answer of 3.02 meters per second squared. And that's your acceleration. Now for D, determine the rotational energy of the drum after 2 seconds. So we know that the system starts at rest, right? And we know that the rotational energy is the kinetic energy. So T is equal to half I omega squared, right? Well, we have I. What is omega though, right? So we can figure out what omega is. We have a time given to us, 2 seconds. So we can use the fact that omega is equal to acceleration times time. So alpha t. So we get a half I alpha t squared, like so, right? And then this is equal to a half 18.15. Alpha is 7.56. 7.56 times 2 squared, like this, right? And 7.56 times 2 is 15.12. And after we add all of this together, we get the final kinetic energy. And I'm actually going to change this to K, just because T was used for tension earlier, just so there's no confusion at all, right? We're going to get that our final energy is, so a half 18.15 times this times 2 squared gives us a answer of 2078 joules. And if you wanted to do three significant figures, as you should be doing, or whatever, it's 2.08 joules. This is supposed to be times 10 to the 3. Yeah, 2.08 times 10 to the 3 joules. And that is how you solve question 1. So that was a pretty easy question, right? Just basically just plug and chug some formulas and then use your free body diagram, kinetic diagram, right? So on to the next question, question 2 over here. A thin-walled hollow cylinder of radius r is released on the horizontal rough surface. This means there's friction, right? With an initial center of mass velocity v. The vertical ramp has a radius of capital R. The cylinder rolls without slipping. So those are all things to keep in mind, right? Anyways, at which angle theta from the measured from the vertical line, so as they've displayed here, would the cylinder stop? What is the, and then, yeah. So this is going to be a interesting question, right? So for A, there's like no numbers in this. There's, well, there's at the end, but not really, right? So anyways, we get that, we start with the, conservation of energy, because we know that the energy here will equal to the energy at the end, which will help us get our angle. So we have that T1 plus V1 is equal to T2 plus V2, right? Well, here we know that V1 is 0, so we can eliminate that, right? And we know that T2 is 0. So we just get this relation here, right? So we know that T1 is a, it's a mixture of rotational and translational energy. So we have half mv squared plus a half I omega squared is equal to mgh, right? That is what, yeah. But what is h, right? Well, h is just, as you can see, the height changes and the height of the center of mass, right? So it's dependent on r. So h is just capital R minus r to the center. And we also need to factor in this cosine term, right? Using some trig, which we have 1 minus cosine theta is how you get it. Now we can also simplify this T1, right? We know that I is equal to mr squared. And we know that omega is equal to v over r, right? Like so. So if we were to make this change, right, we have half m v squared plus a half mr squared v over r squared, right? And this is equal to T1. And I'm going to get rid of the subscripts here because these don't matter anymore, right? What do you notice? Well, r squared cancels with r squared, and now we have half mv squared plus half mv squared. So this is just equal to mv squared after simplification. So we get mv squared is equal to this term on the right, which is our potential energy, right? Because we're looking for the center, So now we are solving for theta, right? Which means we're just going to divide v squared. V squared we're going to divide by gr minus r, like so, right? And then we're going to just do 1 minus. This is equal to cosine theta. And if we want theta itself, we're going to take the inverse cosine, or the arc cos of this term, 1 minus v squared over gr minus r, right, is equal to theta. And that is how you solve that question, right? And this is like there's no numbers in this. This is a theory question kind of thing, right? But we'll get some numbers here now. B, what is the minimum initial speed required to reach theta equals pi over 2. So we're going to go back to this equation for that, right? And we're going to plug in theta equals pi over 2. Cosine of pi over 2 is 0, right? So we're going to get 0 is equal to this term, right? Well, we're just going to add this term onto both sides. So we're going to have v squared is equal to 1. And then we're going to multiply by this gr minus r, right? And then we're going to take the square root. So v is equal to the square root of gr minus r, like so. And that is the minimum initial speed. Now, if you want to specify, and because this is speed, not velocity, there's not going to be any signage and stuff. So you're just going to take the positive root, not the negative root, because it is the speed. And speed is a magnitude, right? So those are the first two questions for this chapter. Very straightforward, obviously. Anyways, let's move on to the next one. So the flywheel has a diameter of 600 millimeters and rotates with increasing speed about its z-axis shaft. When point P on the rim crosses the y-axis with theta equals 90 degrees, it has an acceleration given by a equals negative 1.8 I minus 4.8 j. For this instant, determine the angular velocity and angular acceleration of the flywheel. So this question is still very easy. Actually, it looks intimidating, right? But it's not. So first of all, we need to keep in mind this is diameter of 600 millimeters, right? So its radius is going to be half, so 300 millimeters, and then convert that to meters. We're going to have 0.3 meters is our radius, right? So always put yourself into SI units when doing these questions. And then we get that A is equal to negative 1.8 I minus 4.8 j, right? And we know that these are actually its normal and tangential components, right? So if these are normal and tangential components, what does that mean for us, right? So if we look here, we have these relationships, right? We have these relationships. So we're going to use them. So we have that negative 1.8, which is AT. Remember, I is the tangential and J is the normal. Negative 1.8 is equal to alpha R. So alpha is just going to be equal to, well, R is 0.3. So negative 1.8 divided by 0.3 is going to give you negative 6 radians per second is equal to alpha, right? And then whatchamacallit? Sorry, I'm blanking right now. That's it, right? But we can ignore the negative because we take the magnitude of this. That's all. And then for omega, so we have this for omega. So we know that 4.8 is equal to omega squared r. So we just go 4.8 over divided by 0.3 equal to 16, and then take the square root of 16. So we get 4 radians per second is equal to omega, right? That's an easy question. That is all there is to it. So, yeah. Okay. Yeah, there was a weird cut. I had to get more questions because these ones were really easy. So I've gotten some more challenging questions. There was that other one as well that is gone now, but that was like a really, really easy question. So I didn't want to waste time on something that you could just easily solve. I guess I didn't actually show it for you to actually solve it, but it's fine. No need to worry about that. We have these more difficult questions now, right? So we're gonna, we're gonna have these questions, and I don't like that it does that. Bring to front. There we go. So this question: the circular disk rotates with a constant angular velocity omega equals 40 radians per second about its axis, which is inclined in the YZ plane at the angle theta equals tan inverse of 3/4. Determine the vector expressions for the velocity and acceleration of point P, right here, whose position vector at the instant shown is r equals 15I plus 16j minus 12k. Check the magnitude of your results from the scalar values. V equals r omega and an equals r omega squared. So what are we looking for? Velocity and acceleration vectors at P. So there are some. First we need to draw, because this is an interesting shape, right? So we have this like disk thing, and then we have our z-axis, we have our y-axis off this way, and we have our x-axis off this way, right? And that's just a copy of what we have there. So we know that we have this here, which is offset at angle theta. And we know that P is right here, right? So, and this arrow, by the way, represents a unit vector in the direction of where our, the direction of this, which is the center of where our angular velocity is, right? And keep in mind, this is only in the YZ plane. So this is 2D. So to denote our unit vector, we're going to call that u. It's equal to, so if it's only in the YZ plane, right, 0I plus, well, let's look at it now. Y is our opposite, right? If we were to put our angle here as well, we could put it like that to have two triangles. This is also theta, right? Y is our opposite. So sine theta j, that's not how you spell theta. Sine theta j, and then z is cosine theta, right? Plus cosine theta k. So to get theta, we're told that it's equal to the arctan of 3/4, which you can just put that into your calculator, and that gives you arctan of 3/4 is 37 degrees, right? So if we take the sine of this angle, we get, so sine of 37 is equal to 0.6, and then cosine of 37 is equal to, we take the cosine of this, we're going to get approximately, we take the cosine of this angle, and we're going to get a nice clean 0.8. No approximately's. I just, I plugged into my calculator wrong. So that means u is equal to 0.6j plus 0.8k. So now that we have our unit vector, we can get the vector for the angular velocity. And to do that, right, we will just go u times omega. So u omega is equal to omega, I guess, right? I'm going to change this into a lowercase w, and I'll write that here, w, right? To denote that this is not the vector, and this omega is the vector. So this is just going to be equal to, so it's 40 radians per second. So 40 times 0.6 and 40 times 0.8, we're going to get that it's equal to 24j plus 32k, and this is in radians per second. So to get our velocity vector, we just have to do v is equal to omega cross r. And we have a position vector, which is what r is. So I'm going to write that out here, right? We have omega cross r is equal to ijk, and these are supposed to be hats, not dots, ijk, and then we have 0 24, and 32. And then for the position vector, we had 15, 16, negative 12. 15, 16, negative 12, right? And then when doing a cross product, it's just I is this, and then for j, it's going to be this and this. Right, that's for I, and then for j, it's going to be this minus this, negative in front, and then for k, it's going to be this minus this, negative in front, or no negative in front, right? And then I is like this, right? So computing all that, we're going to get v is equal to, so we're going to have 24 times negative 12 minus 32 times 16 minus, because it's the j, and this is I, minus, we're going to have 0 minus 32 times 15, right? So the negatives are going to cancel. This is j, plus we're going to have 0 minus 24 times 15. That's your cross product. So we're going to get v is equal to, so getting all these terms is going to be, let's see in the calculator. So this is a negative 800i plus 480j minus 360k. And this is inches per second, right? Did it say inches? No. I don't know where I got inches from. Whatever. This is meters per second. Meters per second. I don't know where the inches came from. So we know that angular acceleration here. So alpha is equal to 0, right? Now, the reason for this is the angular velocity is constant, as mentioned here. And constant angular velocity means that you have no angular acceleration, right? So we know that this is equal to 0. So that means the, and remember we're in like the normal and tangential stuff, right? So we know that the binormal acceleration is equal to 0 as well, right? I don't know why I put two equal signs. This should be like a, therefore, yeah, there we go. Therefore, alpha over, or binormal acceleration is equal to 0. But since the angular velocity vector is not 0, there is going to be a normal acceleration. And we know that an is just omega cross r, right? But we already computed omega cross r. So this is just omega cross v, right? And now we're going to write that here. Omega cross v is equal to I, j, k, like so. And we know that omega is 0, 24, 32. And then v is negative 800, 480, and negative 360, right? So if we were to write this out, we get that an is equal to, and you can write down an as just a because it's the only acceleration we have, right? So if you wanted to just denote it as a, you could. But if you were to write it out, we'd get negative 24 times 360. This is supposed to be 24 times negative 360. Oops. 24 times negative 360 minus, and then we get 32 times 480. 32 times 480 minus, because it's j, 0 minus, so 0 minus 30 times negative 800. I forgot the 0. 0 minus, and then plus, in the k, we have 0 minus negative 24. 24 times negative 800, right? As you can see, we have some negatives as canceled. So this is negative minus positive. So that stays, well, it could become positive depending on the number. And then this is negative, 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 triple negative. So this stays negative. And then this is double negative. So this becomes positive. So we're going to get finally that an is equal to negative 24,000 I, right? And then we're going to have minus 25,600 J. And then the K is 24 times 800 is 19,200 K. And this is meters per second squared. And that's the question. You can, if you want to, on your own, check the magnitude of your results from the scalar values V is equal to R omega and AN is equal to R omega squared. How you would get that is, well, you already have omega as a scalar. You would just do the normalization thing. Like you would take the square root of all the terms. So 15 squared plus 16 squared plus 12 squared, and then take the square root of that to get the magnitude of R. And then you do the same thing for V and AN, and then you just do your multiplications to check. I'm not going to do that because that's a waste of time. Well, it's not a waste of time, but it's a waste of time for me to... It's not a waste of time. I don't know why I said that twice. You can check the answer if you want, right? But these are the correct numbers. Now on to this question, right? So this is Q5. The rigid link moves from position ABC to position A prime, B prime, C prime, while end A moves 40 inches to the left with constant velocity V equals 10 inches per second. Determine the average angular velocity of the arm BC during this interval. Assume counterclockwise motion. Now, what do we know? Well, we know that A has pure translation, and then BC is rotating this way. There's a rotation about B like this, right? That is what we know about this question. So let us, let's just diagram this here quickly, right? So we have that translation A, B, C, and I know this is not, you know, like how it is originally, but we're going to ignore that for this diagram because we're only looking at the translation. Well, and then this is A prime, B prime, C prime. So A prime, B prime, C prime, right? It translates like this, 40 inches, right? And this is T for translation. Now, if you look at the rotation it goes through, we have A, B, C, and now this is actually drawn correctly. A, B, and C, right? Well, it rotates some angle theta about B. This is some angle theta to B. This is a 90-degree angle. And then C, like so, also goes some angle theta, like so. Basically, you can say that the rotation is occurring around B. This is A, B, and C in their new locations, right? So now that we've gotten this visually, we can now look at the solution. And what are we solving for again? The average angular acceleration of the arm BC. So we need to break it down into translational, what you want to call it? Translational and rotational components. So for translational, we have the velocity of A is equal to d over t, right? Because if you look at it, this is a purely x translation. Well, we have that the velocity is 10 inches per second, and we have the distance is 40 inches. So we can solve for t here. So we just get that t is equal to 40 over 10, also known as 4 seconds, right? Now we know the total time it took, and this is purely in the translational. Now we can look at rotational, right? So the angular displacement of A and B, right, are going to be the same. Like this A has rotated, but it's just not visually rotated because, well, the rotation just doesn't look like that, right? But it's easier to solve for B because it rotated 90 degrees, right? From here to here. You just want like this, 90-degree rotation, if you look at it. So we already know that, 90-degree rotation, or pi over 2 radians, right? So we know that omega is equal to theta over t, right? Radians per second, or degrees per second, whichever one you prefer. So we know that it rotated pi radians, right? Or sorry, pi over 2 radians in 4 seconds. So we have this double division, and when you have a double division, you combine them, and we get pi over 8 radians per second is our rotational angular velocity. Now, plugging this into our calculator to get an exact number, we get pi over 8 is equal to 0.393 radians per second as our average rotational angular velocity. And that is that question. That's how you solve that question. And those are all the problems I have for chapter 11, right? There was also this problem here, which touched on chapter 12 content, right? So as you can see, the questions, they are pretty straightforward still. Especially this one was just this. The difficult part is understanding the motion and stuff, right? Like numerically, this was an easy question. V is equal to d over t, and then omega is equal to theta over t. That's laughable. But understanding the motion is really what you need to focus on for these questions. Because if you don't know what kind of motion's happening, you're not going to be able to get the right answer, right? So that's all there is for these problems. Thank you for watching. Hope you learned something, and bye.